Linear equations, systems, and matrices. Today we are going to learn how linear equations work, how systems of linear equations are formed, and how these systems can be represented using matrices. We will start with a single linear equation. A linear equation in two variables has the form ax plus by equals c, where a, b, and c are constants, and x and y are variables. This equation represents a straight line in the coordinate plane. Every pair x, y that satisfies the equation lies on that line. For example, 2x plus y equals 5 is a linear equation. If x equals 2, then y equals 1 because 2 times 2 plus 1 equals 5. So the point 2, 1 lies on the line. If x equals 0, then y equals 5, so 0, 5 is also on the line. Each linear equation has infinitely many solutions. Now let us consider systems of linear equations. A system is just a collection of linear equations that share the same variables. For example, 2x plus y equals 5x, y equals 1. This is a system of two equations in two variables. We are no longer interested in all solutions to each equation separately. We are looking for values of x and y that satisfy both equations at the same time. Geometrically, each equation represents a line. The solution to the system is the point where the two lines intersect. Let us solve this system. From the second equation, xy equals 1, we can solve for y. Y equals x1. Substitute this into the first equation. 2x x1 equals 5, 3, x1 equals 5. 3x equals 6x equals 2, then y equals 2, 1 equals 1. So the solution is 2, 1. Now we introduce matrices. A matrix is a rectangular array of numbers. For example, 1, 2, 3, 4 is a 2 by 2 matrix. Matrices are extremely useful for organizing and solving systems of equations. To see how this works, take the system 2x plus y equals 5xy equals 1. We separate the coefficients of x and y, the variables, and the constants. The coefficient matrix is 2, 1, 1, 1. The variable vector is x, y. The constant vector is 5, 1. We write the system in matrix form as 2, 1, x equals 5, 1, 1, y, 1. This is called a matrix equation. It represents the same information as the original system, just written more compactly. To solve systems using matrices, we use row operations. These operations do not change the solution of the system. The three allowed row operations are swap two rows, multiply a row by a non-zero number, add a multiple of one row to another row. We apply these to the augmented matrix. The augmented matrix includes the constants 2, 1, 5, 1, 1, 1. Now we simplify. First, swap the rows so the leading coefficient is easier to work with. 1, 1, 1, 2, 1, 5. Now eliminate the 2 under the first. 1. Multiply the first row by 2 and add it to the second row. Row 2 equals row 2 to row 1. 1, 1, 1, 0, 3, 3. Now divide the second row by 3. 1, 1, 1, 0, 1, 1. Now eliminate the 1 above the 1. Add row 2 to row 1, 1, 0, 2, 0, 1, 1. This matrix corresponds to x equals 2 equals 1, which matches our earlier solution. This method is called Gaussian elimination. It allows us to solve large systems of equations efficiently. Matrices are not just bookkeeping tools. They describe transformations, data, and physical systems. In engineering, they model circuits. In physics, they model forces and motion. In economics, they model supply and demand. In computer science, they power graphics and machine learning. Every system of linear equations can be written as a matrix equation. Every matrix equation represents a system of linear equations. That is why matrices are one of the most important tools in modern mathematics.